Okay guys, in this video we're going to be talking about reaction mechanisms for chemical kinetics, and we're going to introduce the idea of an elementary reaction step, okay, which is distinct from a stoichiometric chemical reaction. You can classify elementary reaction steps according to their molecularity, and given the molecularity of an elementary reaction step, you can write out the rate law for that reaction step. You'll see what I mean when we go through the examples. And there's some other things that we can do with the reaction steps for a mechanism, and so I'll go through those. So this first slide is meant to distinguish between stoichiometric chemical reactions and elementary reactions. So stoichiometric reactions are really only a before and after shot of a given chemical transformation. So you have some overall process that takes you from your initial set of reactants to your products. However, the stoichiometric chemical equation doesn't tell you what's happening in between the reactants and products. It's just what you start with and what you end with. Now, the reaction mechanism is an identification of all of the steps that take place in that stoichiometric process. It could be just one step, or it could be 100 steps. Okay? The stoichiometric chemical equation doesn't tell you otherwise. The mechanism, however, specifies everything. Okay? Usually reactions proceed through, well, at least one, of course, but often they proceed through multiple elementary reaction steps. Okay, and so the mechanism specifies what those steps are. What an elementary step is it represents a single molecular collision event. So a fundamental physical event that occurs, two reactants collide with one another. It's very common. Or you can have one reactant falling apart into products. But it's an actual event that occurs. It's not just a before and after shot. It's the process that actually is undertaken. So let's just go through a quick example of a simple mechanism. So here we're talking about the decomposition of ozone to oxygen gas. One way of thinking about it is a simple two-step reaction mechanism where an excited ozone molecule falls apart into oxygen gas, diatomic, and an oxygen radical. That oxygen radical can then go on to react with another ozone molecule, and causing it to break up and give you two more products. Okay, so this is a two-step mechanism. It involves a species called an intermediate. The oxygen radical in this case is the intermediate. An intermediate is a species that is produced in one step of the mechanism and then consumed in a later step, and that does not appear in the stoichiometric reaction. Okay, so in these two reaction steps, an ozone molecule falls apart into these two species. In the second step, an oxygen radical collides with an ozone atom, or ozone molecule, and then you get two oxygen products out of it. So these are definite chemical events, whereas what we see in the stoichiometric chemical reaction is just what we have at the beginning and just what we have at the end, okay? Without any knowledge of what happens in between. So there's a difference between stoichiometric chemical equations and elementary steps. The molecularity is used to classify different elementary reaction steps. So an elementary reaction with only one reactant is called unimolecular. And the reason I have a star here, it's meant to highlight that the ozone molecule needs to be excited in order to decompose. You have one reactant, and so we would classify this, if it is an elementary step, as a unimolecular reaction. When you have two reactants colliding with one another, it's said to be bimolecular. And so here we have two NO2 molecules colliding. You get an NO3 product and a nitrogen monoxide molecule. This is bimolecular because two things collide. Here we have termolecular. Three things are colliding together, two bromine atoms and an argon. This is not a very common situation, but they do occur. This is called a recombination reaction. Tetramolecular and higher order collisions have never been observed in nature. So Term molecular is already somewhat rare, and then 4 things coming together to actually react, or more things, just doesn't occur in nature. It's never been observed to really be a significant part of any natural reactions. One of the other features of elementary reactions, because they correspond directly to chemical events, unique chemical events, you can derive the rate law from the reaction for the elementary step. Okay, you can't do that for stoichiometric reactions. I had warned you about that in previous videos. However, for elementary reaction steps, because what you see is what you get, you can derive the rate law from their chemical equations. Unimolecular reactions are first order. Okay, so when one species appears on the reactants, you increase the order for that reactant by a factor of 1. So if it appears once, you get a first order reaction. For bimolecular reactions, there's 2 types. In type 1 bimolecular reactions, the species that are reacting are both the same. Okay? Each time the species appears as a reactant, you increase the order of its contribution to the rate law. So since you have species A contributing twice to the reactants in the type 1 reaction, the reaction winds up being second order in species A, and of course it's second order overall. In this bimolecular type 2 reaction, here the 2 reactants are different from one another. A plus B are assumed to be different species. Each species appears once in the reactants, and so it's first order in each species in the rate law. Second order overall, though. For termolecular, there's 3 types. I'll write them down. You can have each species being the same, so this would be type 1. Here you would have that the rate is equal to some rate constant, and it would be a to the 3rd. You could have 2 species being the same and the 3rd one being different. This would be the type 2 termolecular a squared b. And then the 3rd one you see here, this would be the termolecular type 3 reaction, where each species is different. And so it would be first order in each of them. If you have the correct mechanism for a particular reaction, you can derive the observed rate law. Unfortunately, if you have the incorrect mechanism, you can also derive a rate law, but it may not be the observed one. But sometimes it could be. So you can have 2 distinct mechanisms that actually give the same rate law, which is confusing. Which mechanism is correct? Well, you don't know. You have to do more experiments to show that. So proving mechanisms is tough business, okay? And so mechanisms are typically only accepted on a provisional basis, that is, until the next experiment comes along to show that it's incorrect. It's tough because you can't observe the mechanisms directly. You've got to do things indirectly with lots of different experiments. So different mechanisms are proposed and tested against the experimental data. Since different mechanisms don't necessarily give a unique rate law, it's difficult to prove a mechanism. You know, there could always be some intermediate that you weren't able to detect hanging around, which means that the mechanism is actually different than what you think it is. One of the important rules when thinking about how to derive the mechanism or to derive the observed rate law from the mechanism of a reaction is the idea of a rate determining step, which means that the slowest step generally in a reaction mechanism is usually the one that determines the observed rate law and the observed rate constant. So, for example, in this reaction here, this is a stoichiometric reaction involving the reaction of NO2 and fluorine. This is the observed rate law, first order in each species. The mechanism is given here. Okay, so you've got NO2 collides with the fluorine. It gives you this one of your products and then a fluorine radical, which then goes on to react with another reactant, and that gives you your second radical. It's known that the first step here is slow and that the second step is fast, meaning they have very different rate constants. And the one with the smaller rate constant is the slow step. It's the rate determining step. And so this is the observed rate law for the reaction. The slow step always determines what you observe in the rate law. And so by comparing this rate for this slow step to the observed rate constant, you can identify the observed rate constant with the value of K1. Let's look at another case. This one involves a mechanism that has a pre-equilibrium step, which is kind of interesting. So here's our stoichiometric reaction. It's the decomposition of dinitrogen pentoxide into NO2 and O2 products. It has this mechanism. So you have a reversible first step. Okay, so the dinitrogen pentoxide can fall apart into NO2 and NO3. NO2 and NO3 can recombine to form the dinitrogen pentoxide. And this is a fast process. So this process comes to equilibrium before really steps 2 and 3 can get going. Okay? In steps 2, NO2 reacts with NO3, you form this nitrogen monoxide and one of your products. Also you get the O2 product, and then the nitrogen monoxide intermediate can then react with an NO3 to give you more of your products, to give you the other two equivalencies of your products. And so we've got essentially a total of 4 steps. We've got the forward step, the backward step, and then these 2 steps as well. The K minus one, it's a notation that's used to mean it's the reverse of this forward step. So this is fast. The slow step in this mechanism is known to be this middle step. Okay, and so here the rate of the reaction would then be decided by this rate. And so for this elementary step, we see that it's bimolecular, type 2. So the rate is going to be equal to K2. NO2 appears once, so it's first order. NO3 appears once, so it's first order there. And so compare this rate law from the mechanism to the observed rate law, which is first order in N2O5. And you think to yourself, well, gosh, this rate law is kind of weird. I mean, it involves a product, and then it involves an intermediate, and that's nothing like what I have here for the observed rate law. So the question is how do I take this rate determining rate law and convert it into the observed rate law? And so we exploit the pre-equilibrium part of the mechanism here. So what an equilibrium means from a kinetics perspective is that the forward reaction rate equals the reverse reaction rate. So this is an elementary step. The forward rate is going to be the rate constant times the concentration of the dinitrogen pentoxide, and the reverse rate will be the reverse rate constant times the concentration of each of the reactants. Okay? Once this reaction comes to equilibrium, the forward rate equals the backward rate, and so we can set them equal to each other and solve for the intermediate concentration. I'm going to go ahead and do that. I'm going to take this forward rate, I'm going to set it equal to the reverse rate, and I'm going to use that to eliminate the intermediate concentration. So I'll write that NO3 is going to be K1 into O5 divided by K minus 1 NO2. And now this guy can get substituted into the rate law. I'm going to go ahead and do that too. So we'll have rate equals K2 NO2 NO3. We'll substitute in our pre-equilibrium expression for the NO3 intermediate. What happens? The NO2 cancels, and we wind up with this K1, K2 over K minus 1 times N2O5. And what we'll do then is we'll call this K observed. And so we see that this rate, here I should have put that 3 right there, we'll see that this rate, even though it doesn't look like it's the observed rate law, it actually is after a little bit of algebra. And so that's how you derive the observed rate law from the mechanism. And in this case, we have a pre-equilibrium step. The observed rate constant we see is a combination of rate constants from the mechanism. And that's a very common feature in chemical kinetics. So, should we put it into practice here? So let's play around with a complicated mechanism. So we've got this complicated mechanism. It involves the decomposition of nitrile chloride, and we're being asked to determine the overall reaction. So what's the stoichiometric reaction? Well, if you have a valid mechanism, or I should say that every valid mechanism should allow you to derive the stoichiometric reaction by simply adding together all of the species. So what I'm going to do is I'm going to take all of the reactants and put them on one side of the chemical equation, take all of the products and put them on the other side, and I'm going to watch species cancel out. Okay? So we've got 2NO2Cl plus N2O plus ClO2 plus NOCl plus ClO. Then I'm going to take all the products, ClO2 plus N2O plus ClO plus NO2 plus NOCl plus NO2 plus Cl2. It's tough to fit them all. I guess I got it. And now what we want to do is cancel things that appear on both sides. So right away I see those guys cancel. See that one cancels. I see this one cancels. That one. This one cancels. I wind up with 2NO2 Cl. We get 2NO2 plus Cl2. So that is the balanced stoichiometric equation. All of the things that canceled out, those are all intermediate species. Okay, so the N2O, the ClO2, the ClO, these are the intermediates in the chemical reaction. They don't appear in the overall stoichiometric reaction. Okay, now we're being asked to write out the rate law expression for each elementary reaction. Well, that'll be fun. So let's do the rate law for the forward step. So we'll have rate for the forward step is going to be the rate constant. We see that it's bimolecular type 1, so we're going to wind up with NO2Cl squared. We can also do the reverse step. Rate minus 1 will be the reverse rate constant. Here we see that this is a termolecular reaction going in reverse. N2O, ClO. What about for this fast step? It's also reversible. Rate 2, K2, the rate constant, bimolecular type 2. Right? Each of these species appears once, and so it appears once in the rate law. We've also got the minus 2. So K minus 2. Also bimolecular type 2. Bimolecular type 2 is the most common type of reaction step. Then we've got K, the third, the slow step, which will be the rate limiting step. Rate 3, K3, NOCl, ClO. Right? So this is what would determine the overall rate. But notice it's in terms of intermediates, which isn't very helpful. We really would like to express the reaction rate in terms of reactants. And so we want to get rid of those if we can. Well, because the two pre-equilibrium steps are fast, we can equate the forward rate to the backward rate here and the forward rate to the backward rate here. When you do that, you can solve this first equation, you can solve it for CLO. This first pair of equations you can solve for CLO, and for the second pair of equations you can solve for NO. Okay, so what I'm going to do is I'm going to set this equal to that and solve for CLO. And so you get K1 NO2 Cl squared over K minus 1 ClO2 into O. Okay, so that's the expression, the pre-equilibrium expression for this intermediate. You can do the same thing here. Set this equal to that, solve for the NOCl. Okay, that's the intermediate, that's the pre-equilibrium expression for that intermediate. Now we take these two guys and we plug them in here. And we're going to get some cool cancellations. So we'll have K2 into O, ClO2, now substitute in the ClO. And we're going to find some things that are going to cancel out. So we see that that dude cancels this one cancels that one, and that's it. That's all we got. So now what we'll do is we'll collect the rate constants over here. It's going to be K1, K2, K3 over K minus 1, K minus 2, and then we've got NO2Cl squared over NO2, and that's our rate law. So for this one, it's a complex mechanism, and you get a complex rate law. So it winds up, this would be our observed rate constant. It's second order in the reactant, but it also depends upon the product concentration. And so not all reactions have simple rate laws like we've studied previously. Complicated mechanisms have complex rate laws. Here's another example. This one's a little simpler, although I don't think I can work it because I forgot to show which one is fast or slow. We can do a couple of things with this problem. We can write out the overall reaction. So I can take the reactants and write them together. Cl plus O3 plus ClO plus O. Put all the products on the same side. Let's see what cancels out. Cl plus, did I miss one? No. Those cancel out. Yeah. So O3 plus oxygen gives you two O2s. That worked out. So the one thing about this mechanism, it's kind of interesting. There's both reaction intermediates and what's called a catalyst. So the reaction intermediate is a species that is produced and then consumed. Notice that this first step produces the ClO, then the ClO is consumed, and it doesn't appear in the overall reaction. A catalyst is a species that is consumed and then reproduced and doesn't appear in the overall reaction. The chlorine fits that bill. Look, the chlorine is consumed in the first step, and then it's recycled in the second step, and it doesn't appear in the overall chemical equation. So the chlorine is a catalyst, whereas the chlorine monoxide is a reaction intermediate. Now, I don't have the relative speed of the two reactions, and so I can't really comment on which one is fast or slow. I'm guessing that the slow step is probably the first step, but since I don't know that for sure, I'm gonna continue. Well, I'm going to stop is what I'm going to do. So I'm going to stop right here, and we'll pick up with the catalysis in the next video.